So a very good day to Dr. Lim. Today we will be presenting about atomic excitation. So my name is Goh Yong Shen, my matrix number is 197444, and
my name is Munawwarah binti Khalid, and my matrix number is 198343.
So without further ado, I would like to pass the time to Muna to explain about atomic excitation.
Okay, so for atomic excitation, there are actually two ways on how to excite an atom. So this is the basic principle of atomic excitation. So atoms can absorb and also emit energy by jumping to different energy levels, hence the ground state and also excited states. So yeah, it can be excited to its excited state. So I'm going to explain further after this. So there are mainly two ways on how to excite an atom. So the first one is the collision between particles. So what happens is that they supply electrons and also atomic ions, and they try to collide both of these together. So what happens is that the electron loses energy and hence it excites the atom to its excited state. So the kinetic energy from the electrons, so the electron is moving, hence it has kinetic energy. And then the kinetic energy will be transferred, when they collide, the kinetic energy will be transferred to the atom, hence bringing the atom to its excited state. And then the energy needed for this atom to be excited is equivalent to the energy, the difference in energy from its ground state, n equals to 1, to n equals to 2, its excited state. So the electron need to have enough kinetic energy and equivalent to the difference in energy between these two states. So that is one of the ways. So this is the graphic representation on how particles collision happens. So they have two atoms, and they collide these two atoms together, and the kinetic energy from this collision will be absorbed by one of these atoms, hence bringing it into its excited state. So this is the roughly the process of collision between particles, how it can excite an atom. So an experiment was conducted by James Franck and also Gustav Hertz in 1914 that explains this process. So what they did is first they supplied the electrons with a voltage, so it accelerates these electrons into a cloud of mercury atoms. So as you can see, this is the output from the experiment. So as they increase in voltage, as they supply increasing voltage, the current will also increase, which means that the electrons increases in its speed. So the speed of the electron will be increasing until it reaches to a point where the graph drops sharply. So what happens during this phase is that the electrons loses energy when it collides with a mercury atom. So when it collides, it loses energy and transfers the energy into the mercury atom, hence bringing the mercury atom into its excited state. And this collision is inelastic because the momentum is not conserved. So what happens to the mercury atom after it's being excited? It will remain in its excited state for about 10 to the power negative 8 seconds, and then return to its ground state by releasing energy, which is in the form of photons. So as you can see, for a specific atom, and in this case mercury atom, we need around 4.9 electron volts of energy in order to bring one atomic and one mercury atoms to its excited state. So after they have transferred the energy, then the current will go back, the graph of the current will decrease, and then it will continue to increase as we supply more voltage to the experiment, and then the current will keep on increasing until it reaches another peak, and this time it is 5.8 electron volt in order to excite another mercury atom. So this is the findings of the experiment. So this proves that electrons can be excited through collisions, and also proves that there exists an energy level and that it is discrete inside every atom. So the second way on how to excite a photon is an atom is through photon excitations. So what happens is that we supply a photon, and since photon is an EM wave, it carries momentum and also energy. So it supplies the photons onto an atom, and then this atom absorbs this energy, thus bringing it to its excited state. So once it's excited, it stays there around 10 to the power negative 8 seconds, and then return back to its ground state by releasing energy in the form of photon. So yeah.
So now I would like to talk about the contributions of atomic excitation to our society. So one of the first application, or one of the first contribution, is actually atomic spectroscopy. So spectroscopy can be actually defined as the interaction between electronic radiation and matter in the form of atoms, molecules, compounds, etc. So since different atoms have a unique electronic arrangement, the wavelength that they absorb and emitted after excitation will be unique. So this method can be used to determine the constituent elements of any sample and also determine its concentration as well. So there are actually four types of atomic spectroscopy, and we will be discussing about them. So the first way is atomic absorption spectroscopy. So this uses the concept of absorption. So the energy from the light is absorbed by the atom, and the electrons will be excited. The sensor in the machine will actually detect that the intensity of the light will be reduced, and the absorption spectrum will be analyzed. So since each element has a unique absorption spectrum, the constituent element can be determined through this method. The second method is atomic emission spectroscopy, so in which elements are excited through flame, electric arc, or through plasma. So since the electrons are excited, it will fall back down and it will release photons. And the emission spectrum will be analyzed to determine the element. The next one is atomic fluorescence spectroscopy. It combines both concepts from atomic absorption and atomic emission. And however, in this case, the fluorescence of the decaying atom is measured instead. And the last method is X-ray fluorescence, in which high energy particles are collided with the initial electron, and initial electrons will be excited and the X-ray photon will be released. So the X-ray spectrum will be analyzed instead to determine the constituent atoms. So that is the first application. The second application is fluorescence. So fluorescence can be defined as any chemical substances that re-emits light of lower frequency after it absorbs a light of higher frequency. So as you can see here in this energy diagram right here, as electrons from the first electronic state absorb light, it will be excited to the second electronic electronic state. Then it will undergo non-radiative transition. So during this phase, no electromagnetic radiation will be emitted. However, as it starts from the ground state of the second electronic state and it falls back down to the first electronic state, fluorescence will be emitted. So there are actually three different usages of fluorescence, namely optical whiteness, fluorescent lights, and fluorescent tags and nanoparticles. So for optical brightness, it's actually an additive indication. So optical brightness work by absorbing ultraviolet light, okay, and it will re-emit visible light in the blue spectrum of visible light. So the blue visible light actually counteracts the yellow color of your shirt, making your shirt look brighter. Then we have fluorescent lights. So fluorescent lights are mainly used in advertising. So as you can see, noble gases are used, and different noble gases produce different light through electron excitation. And the last one is fluorescent tags. So fluorescent tags are chemical compounds that are attached to biochemicals such as DNA or any protein structure to determine the function and its condition. So these substances will then be exposed to UV light, and the emission will be observed as seen in this picture.
So the next application of atomic excitations is lasers. So laser stands for light amplification by stimulated emission of radiation. So it has this four unique characteristics, which is monochromatic, coherence, intense light, and also can focus highly. So because of this characteristic, it is most significant in medical field, where hospitals use lasers to perform intricate surgeries to cut through small spot and also tissue cells because of its high intensity and can be focused easily. And the next thing, lasers are also used to store information digitally by encoding information on CDs and also DVDs.
So I would like to conclude this presentation by saying that atomic excitation is not only a theoretical matter, it also is very useful towards the average person, as we have stated, through optical brightness to lasers and other applications such as neon lights. So hopefully more research could be done so that it could be applied more extensively in our life. We would like to say thank you very much for listening to our presentation. Thank you.